So, H2 is L'Hopital. So we're going to take you to the Google slides and go over those. Within the textbook, we are up at page 444. What do you have? You have the ratio of two derivatives. By definition of a limit, difference quotient from chapter 2. So now what happens? Well, you have the limit symbol for numerator and denominator. You just put one limit symbol in front of the whole thing. Then what? The x take away a reduces out. Because you're dividing by a fraction. So when you invert and multiply, the x take away is reduced out. I'll tell you why that. Why you invert and multiply fractions, you're left with this. Now, this is a little awkward. The only reason this works is if you look in the book on page 444, he outputted A, and he output for A and F of G is 0. So that's why these are 0. And that takes you to here. Well, what does that mean? It's saying this. You want the limit of this ratio, it's going to be equal to the ratio of the derivatives. So here's an example. So think about this. In order to do this problem, we're back to limits. But in the meantime, we have to cover limits. We covered differentiation. So I want to know how this thing behaves. 1 take away cosine x over x plus x squared. Without a calculator. But you are going to put it in your calculator. Roll it right. You go to y equals your y1. Make sure you put your numerator and denominator in parentheses. Now, think about it. You do this by substitution at 0. The cosine would be root 4 over 2. That's the 0 radius. So you have 1 take away 1 over 0 plus 0 squared. You have 0 over 0. This can't be done by substitution, by putting a 0 over. You're looking at the picture of the graph, yes? You can tell, go to the table, start at 0, and look at your output. You have an error message at 0, what's that? But the question isn't what's the value of the function. The question is what's the limit as x goes to 0. So you can make the judgment about that by looking at the picture of your graph. And what we're doing up here is doing this problem analytically without the picture, without a calculator. It's not a calculator problem. And what did L'Hopital say? It said the limit as x goes to a of f of x over g of x equals the ratio of the derivative. So we differentiate the numerator. The derivative of 1 is 0. The derivative of cosine x is negative sign. So you have to subtract the negative sign. You have sine x at the top. Power rule on the bottom. Now by substitution, you would put, ready, the sign of 0. The y value of 0 is 0, 0 the numerator, divided by 1 plus 2 times 0. So if you don't have 0 over 0 anymore, you have 0 over 1. And if you have 0 in the numerator, the value of your fraction is 0. Done. Okay? So can you see from the graph you drew and from your table that the limit of the graph is 0? That your calculator confirms what's up here. You gotta be careful because of this. L'Hopital is like sunscreen. You can reapply it. But you gotta be careful. Because you can only reapply it if you still get 0 over 0. Or infinity over infinity. So this is telling you better stop. Because if you do it again, look what happens. This would be wrong. You would get cosine x, derivative sine cosine, derivative denominator would be 0 plus 2. You would get 1/2. So you would get a wrong answer. Every time you use L'Hopital, you have to verify either got a numerical answer or you got 0 or 0. You just can't do this with Washington without checking the number of the answers you get in between. Indeterminate. They use the word indeterminate on the textbook or the PowerPoint. Indeterminate means 0 over 0. I don't mean it's all. Those things you can't divide by 0. Now you can. 0 over 0 is indeterminate. Infinity over infinity is indeterminate. Look at this mess. By substitution, what do we get? Root 1 is 1, take away 1 is 0. Subtract 0 in the numerator. 0 subtract 0 is 0 squared. That's 0 over 0. Okay? And again, we could ask you to graph this, and you would see by the graph is limited. But the point being, you did it for the person. This is a non-calculator issue over time. And traditionally, half of the AP tests you have a calculator. Now, last year, you're welcome to use a calculator for the whole 45 minutes. But it's an exception. So you rewrote it, the fractional exponent, here's the derivative. Power rule, du is a 1, derivative of 1 is 0, derivative that's 1/2. Power rule, put 0 in here. You would have, right? 1 to negative 1/2 power is 1. 1/2, take away 1/2 is 0, 2 times 0 is 0. So in this case, you got 0 over 0 the second time. You can do L'Hopital again. And you get a value. So that means the limit of this graph as x goes to 0, as x goes to 0, it's trying to get to a height of negative 1/8. But that's the problem without seeing the picture. Now, these are all considered indeterminate. This is like, infinity over infinity is like 0 to 0. We're good to go. If you have any of these forms, you have one step you have to do first, which is you have to manipulate the problem algebraic. It has to look like this, or this, in order to apply over top. So these don't make sense. They're indeterminate. And there's just an algebra step before you rewrite it to look like this, and then you apply the formula. So, we are telling you, ready? There is a book. They just saw the PowerPoint. Example 6, 7, and 8 are these forms. And the algebra will take you 0 to 0. Example 9 and 10 are these indeterminate forms. And the algebra will take you over to infinity over infinity. So we're going to do one problem that's straightforward, and we're going to do one problem that has to be manipulated algebra. Okay? So, example 1. Here's the work. Ready? We put 0 in here. So you would get the square root of 1, take away 1, 0 over 0. Indeterminate, you can't tell. The height of this graph is x goes to 0. So we load the column. And you get, right, the derivative, 1/2 mu du. 1/2 this to the negative 1/2, derivative, what's inside there is 1. So you would get 1/2 times this amount in the denominator. This thing is 1. Now you put 0 here, you would get 1/2, which is telling you what? That as x goes to 0, this graph is trying to get to 1/2. So we go in here and say, all right, it's the square root of 1 plus x take away 1. The square root 1 plus x take away 1 divided by x. There's the picture. There's a hole in the graph here, but the height is trying to get the 1/2 from the left and from the right. But what this is doing for you is saying how to answer this question mathematically. If you go back here, look at the table. Start at 0, make the delta table small, make it 100. Then we see how this graph from the left is as you're going down towards 5/10. Right? And from the right, we're going down away from 5/10. Where's the starting with the point? So That's your model. You're going to exam or problem number 3, please. So here's example 3. Now it's not going to 0, it's going to 2. That's not going to really matter. You got 0 over 0. You differentiate this, and you're here. When you put 2 in here, you have 4 to 1 half power, which is 2. 2 times 2 is 4. That's going to a height of 1/4. Not going to get there. That's the limit. As x goes to 2, it's trying to get to a height of 1/4. But there's going to be this possibility there, because when you do that problem, you put 2 in substitution, you get an indeterminate form of 0 over 0. Now, you understand how much easier this would make chapter 2 for you? The limits. The problem is, why do you show this in chapter 2? You have to do differentiation where you work. You didn't have differentiation. So the point is, limits were the foundation for differentiation. And now returning to limits and showing you a more efficient way to find limits like that. Here's example 8. So for example 8, ready? When the limit is x goes to the right without bound. So you have 1 plus 1 over x. As x is really, really large, this thing's going to 0. You have small over 1. Caret x. So this thing is 1 raised to infinity. You want to know, how is this behaving, right? As x goes to the right without bound. And the point is, you have to manipulate this. You can't apply it over top unless it's in the form of 0 over 0 to the infinity. So one thing we could do is we can take the natural log. Why would we think to do that? You take a log of this property of exponents, allows you to bring this x up front. So if I take the log of this thing, the question becomes x times ln of mu. Now what? If I rewrite this x, it's being multiplied by this as 1 over x in the denominator. Look what you have. The top becomes the natural log of 1 plus small over large. What exponent you raise e to give you 1? 0. The denominator, small over large. 0. This is now in the form of 0 over 0. You can apply it up top. So what I have is the natural log of mu. What's the derivative? 1 over mu du. What's the derivative of 1 over x? That's x in negative 1. It's negative x in negative second. So what would happen? These would reduce. Right? You would have this. Now what? You have 1 divided by 1 plus small over large. You have 1. That means the natural log of your answer, because you introduced ln, the natural log of your answer is 1. You swirl it. E to 1, e to the first equals what I'm looking for. So the limit as x goes to the right of this ramp is going to a height of e. So when you do this work, gotta be careful, because you get a one. And that would be a multiple choice, that would be choice A, a multiple choice test. The answer is not one, because you introduce LN. So one is the natural log of your answer would be. We're gonna leave that up there, and you're going to problem 21, please. One minute. thought I paused it, I didn't, so. 21, ready? The limit as x goes to 0 of this. E to the 0 power is 1, 1 plus 0. You have 1 over 0, which is large over small, if you have, in effect, 1 going to the fifth. So determine. What did we do? I say E power to the natural log. Well, in the last problem, we took our answer and we swirled it at the end. Here we're swirling it. It doesn't matter. See, E and Ln work against each other. They're inverse functions. So this way is going to take you right to your answer. If you didn't do it this way, you did it the way in example 8, you would get a 2. When you swirl that, you get the second. I end up getting E to the 0 over 0. So I can L'Hopital the exponent. The natural log of mu is 1 over mu du. The derivative of mu is e to the x plus 1. Derivative is denominator is a 1. It would be here. If you put 0 here, you have 1 plus 1 is 2 over 1 plus 0. 2 over 1. Okay, so you're ending up with e to the second. Because all we did was say, use L'Hopital for the exponent. The exponent's 2. The base was e. Your answer is 3. All right. So that is it for 8, 2.